tá dentro do outro ciclo.
Ah, é a mesma conta.
Não funciona tudo igual.
Não, pera, não é uma
Se
conta.
fizer a conta direito, ela é a mesma conta. Sério, mano.
Sério, cara.
Se fizer a conta direito, é só você.
É
a
meio
mesma
da
conta.
hora isso, é bem da
É
hora.
bem da hora.
Será que eu fiz a conta errada? Então eu não copiei do cara do Marcos. Eu quero no Marcos errado.
Então se
Aí
você
você
der
pode
uma
só-
conta, seu bosta.
Mas é muito lógico.
Mas o cara
Não,
do Marcos
é
de intersecção
fácil.
de círculo de fato tem um erro. De fato tem um erro. Ele fala que quando tá vários.
Tem que dar
Não,
um
falta
uma
uma tem dois.
Quem? O que você falou?
O caderno do Marcos falta um dois.
Eu não preciso usar também.
Não.
Tem que dar um.
Ah, aquele bagulho lá que tinha dois no rotate, esse negócio era Atom 2?
Que ele passava dois elementos pra ser de uma ação.
Era um Atom 2 ali dentro.
Mas tem que fazer rotação de vetores.
Não precisa, mas é só rotação de nome integral, não precisa de nada complicado não.
Eu vou colocar a dele, cara. Ah, claro que você tá errado.
É você quem cuidava do seu. Agora eu fiquei meio puto. Porque eu não copiar e eu falei, eu tava errado. Aí eu falei, tipo, eu pensei na hora e parti nesse problema. Eu estava errado. Então eu já sabia. Vamos lá, cara. Caralho.
De quem que é essa coisa?
Soca!
Are we live yet? Yes. Okay. So let's start. So like last lecture, I'll just start talking about problems from yesterday, and then we have time at the end. I'll talk about data structure that you can use to implement your piece. Okay, let's start with problem B. It was a pretty straightforward problem. It had a string of length that most asks. And you need to check whether for all substring of this string, it's reversed also with the substring of the original string. And since the length of the string was 10, which is pretty small, you can just generate all possible substrings, put them in a set, for instance, and then check for each substring whether its reverse also belong to the set. And it was like probably just problem of the context.
Não, eu só achei fácil, tipo.
Problem B, again now versus
Não, eu só achei
dollar.
que isso era igual ao 2021. Calma. Esse não pegou agora.
So in this problem, we had a bunch of attacks.
Ou esse outro pegou?
And for each pair of attacks, you knew whether one would beat the other attack. And this was a game, so Gandalf first chooses one of his attacks. And then the Balrog chooses another attack. And then Gandalf has the choice of changing the attack he first chose. And at the end, we want to know whether Gandalf can win this game or not. So you had to answer this problem whether there was an attack that Gandalf could choose so that no matter which attack the Balrog chooses, Gandalf will always win. And that can only happen if there is some attack that can beat every other attack. Right? And there are many ways of verifying the existence of such attack. One way is to basically keep track for each attack how many attacks it can beat. And well, so in this problem, if we have two attacks I and J, then at first you know that the attack with greater index would beat the attack with lower index. And the problem also gave us some pair of anomalous attacks. So if 2 3 is an anomalous pair, then 2 would actually be 3. So what you could do to calculate the number of attacks each attack beat is to first build this array of how many attacks it can beat, disregarding all those anomalous pairs. So this guy needs no error, this guy needs one attack, 2, 3, 4, so on. And then for each of these anomalous pairs, you can just update the corresponding values. So we know that 2 beats 3, so 2 actually beats 1 extra guys, which goes to 3. 3 beats 1 less attack, so this goes to 2. And then the end you can just check whether there is an attack that beats n minus 1 attacks. Okay. Another way to find one attack that beats any other attack is first you start with the first attack and then you iterate through each other attack. And at any moment you always hold you're holding one candidate of attack. And when you're processing one attack, you just check whether the attack you're holding beats the attack you're looking at now. If this does happen, then you just move to the next attack. If the attack you're looking at beats your current attack, then you discard this one and take this one with you. Okay. And the cool thing is that at the end of this iteration, the attack that you're holding is the only possible candidate for an attack that beats every other attack, right? Because if such attack exists, then at some point, let's say this is the special attack. At some point, I will look at this attack will beat my attack, and then this special attack would also beat all following attacks. So I will be holding this special attack at the end. So you can do this, you can pass through the refers to find one candidate, and then you can check whether this guy actually beats every other attack. So doing this, you know whether the answer is 2 or not. If such a fact doesn't exist, then the answer can only be 1. The answer can never be 0 because, well, the problem is that if the barrel can choose an attack that I cannot beat, then the answer is 0. But that cannot happen because this will imply that the attack that R chose beats every other attack. And we know that this doesn't happen. So the only thing you have to verify is whether a special attack exists. If so, it is unique, so you print 2 at the ID of the attack. If such attack doesn't exist, you just print 1. Alright? Next problem. Delivering phase of problem G. So this was also a fairly easy problem. So you had a grid of lights. Some lights are off, some lights are on. And you're asked to perform exactly K operations. And each operation allows you to pick a row and change the status of every light in this row. And you're asked to maximize the number of lights turned on at the end of all K operations. Well, for each row, it's easy to calculate what will be the resulting number of lights on if you press the corresponding switch. If I press the switch, if I leave it like this, we have 1 light on. If I press the switch, we have 3. We have 1, 2, 2. So let's say that the state of a row is 0 if I can improve my answer by pressing the corresponding switch. So if I change the state of the lights of this row, my answer will improve. So I will say that this is 0. In your case, this is 1, 1, and this doesn't really matter. So suppose that the total number of zeros here is q. If q is less, if k is less than or equal to q, then you can just apply a greedy solution here and just pick the rows with to 0, and such that pressing the switch would increase the most number of slides on. If K is greater than if Q is greater than if K is greater than Q, then you have two cases. Either K and Q have the same parity or they do not. If they do have the same parity, then it's easy to show that you can always there's always one possible sequence of choices that always leads to all rows in state 1. And this is the maximum amount of lights on you can get. And if they have different parities, then this means that at the end, at least one row will end up with being state 0. So you can just find which row would decrease the least your final answer. In this case, it's this one. And this just gives you an answer. So this was a pretty obvious greedy solution. Exactly. Okay, next problem. Problem I. Problem of any colors. So, for problem I, for problem I, we have a sequence of boards, and we want to paint these boards in a specific way that's given the input data. And the operation that we are allowed to do is take k consecutive boards and take the instant color. And the question is whether the given configuration is achievable, and if so, what is the minimum number of operations I need to achieve that configuration? Okay, so it turns out that the conditions for achievability, feasibility, is simply whether there exists a sequence of k consecutive ports in the final configuration, whether there exists a sequence of at least k ports with the same color. Okay. This is a necessary condition because the last time I applied this operation of k consecutive ports will remain, right? So the last operation applied, the boards that I just painted will remain the same color. So we know that the final configuration must contain at least one sequence of k consecutive boards in the same color. If that's not the case, then that configuration is clearly unachievable. If that's not the case, then we can show by construction that the configuration is achievable. And we can do that in the following way. So let's build an auxiliary array that counts for each sequence of consecutive ports. What is the length of this sequence of same color ports? So if I have colors like 1, 2, 1. If these are the colors of the ports, then I will build a second array that will score 2, 3, 1, 1. Okay. I claim that the minimum number of operations need to apply is, let's call it the array we have. The minimum number of operations will always be the sum of k, sigma this. Right. This is clearly a lower bound because this is the least number of operations you need to paint like fi k's of the same color. And what I'm going to prove is that there is a sequence of operations that uses exactly this number of operations that result in this array. Okay. And you can do this in the following way. You just start from the left of the array and really paint the orgs. If I need to paint one org here, and my k equals 3, then I just paint these 3 orgs of color 1. Okay. Once I reach one sequence that has at least k orgs that needs to be painted, I stop. Okay. And then I start painting from right to left. So I need this guy to be painted with color 1, so I paint these 3 guys with color 1. I need this guy to be painted with color 2, so I paint these 3 guys with color 2. And eventually I will reach the same guy that has at least k orgs that needs to be painted. And this segment can be also painted gridly. And you can just, and the number of operations you need to spend here is at least the ceiling of the number over k. And as long as we know, since this guy has at least k words that need to be painted, we can always paint these words so that we do not exceed the k numbers we to the left or the right. So, by construction, we found a sequence operation of this length that paints the column, that words the right ones. So this is the optimal solution. Okay. I call problem C now. Okay. So in this problem, you had a line and had several points on this point. Each point had a certain speed, as I, and we want to make all these points meet at some point. And we wanted to know what is the least amount of time we need so that all points can all meet at the same point. The problem is that you didn't know what is the optimal point. Okay, there are 2 ways to approach this problem. The easy way, which are harder to see, and the hard way, the normal way. The hard way would be to notice that we can binary search on the time that it takes for each work to reach the optimal point. So I can, because if all works can meet in t amount of time, then the works can also meet at any amount of time greater than t. So we can binary search on the optimal value of t to find the answer. Now the question is, how do we check, given the time t, whether the ends can meet in this time? So for each end, we can try to look at what is the region of the plane that this guy can reach in time t. And this is actually a circle, right? this radius is S times TD, I think. I said that physics. So each end will have a certain circle representing the region it can reach. And now, basically, the question is whether these circles have a common point. Right? One common mistake that is a mistake that I also made is to check whether every pair of circles intersect. And that is not enough, right? One very simple counterexample will be this. The intersection of all this circle is the empty set, but oh wait, no, I fucked up.
One circle fully contains one another.
Is that a counterexample? Yeah. Wait, why is that a counterexample?
Because the intersection.
The intersection is this. Got it.
When you say intersection, I think about borders intersection, right?
Yeah, I talk about the area, the whole circle.
Okay.
I'm pretty sure this doesn't work, right? I thought about the counterexample, but it turns out not to be the case.
We can do two side by side and then one over here.
Like this.
Yeah.
The third one direction.
One at the top.
Just like
Yes.
Yeah. I guess it's like should overlap a little bit also, right? Yeah. Okay, we proved that this solution doesn't work. Yeah, I also thought about this at first. I implemented this dot wrong answer and I spent some time trying to figure out why. Yeah, but that doesn't work. So we have to find another approach to check whether all circles intersect or not. So one thing you can notice is that suppose that an intersection exists, right? So there can only be two cases. Either the intersection is a single circle. So in this case, these circles contain every other circle. Or the intersection is something weird like this. I don't know. But the thing is that this intersection is made of arcs of some circles, of more than one circle in particular. So we know that these points are the intersection of two circles, right? Intersection of borders of two different circles. So we can actually check whether there is a point that is contained in every other circle. And this restricts the number of candidates we need to test, right? If you say that that intersection has either one of these two shapes, for this case, we just have to check, for instance, whether every center of circle belongs to the lies inside every other circle. Right? This will mean that the intersection is not empty. And in this case, you can just check whether these intersection points belong to lie inside of every circle. And the number of intersection points is all of them squared. So you could just check every single intersection and see if it lies inside every circle. Right. So by doing this, you could check whether one value of t is feasible or not in cube time. So this will result in an overall complexity of m cubed log something, log of the maximum value. Okay, which should be enough to pass the time limit. The easier approach is a bit harder to see. Well, let's call alpha of t the time it takes for the ith and to reach point xy. So it should be x minus xi. I think this is the distance between 2 points, this is velocity, and so yeah. I think it's correct. Right. The cool thing about this function is that it is complex. It's actually a parabola centered at xi, y. Right. The function that's centered here and grows like this. Okay. Complex functions are cool because you can ternary search on complex equations. Right? If I need to find the minimum value of a complex equation, I can apply ternary search to do that. But this is not the function that I'm trying to minimize. It's the maximum of all fi's. Right? The function that I'm trying to minimize is this. Max. Right. But it turns out that the maximum of complex function is also complex. It's not very hard to prove. But I'm not going to do that. It's really easy. You know that if f is the maximum, that f is greater than any fi. And just do some arithmetic manipulations to reach them too. You have to prove this. Suppose that x and y are points in 2D. So you have to prove that f of tx plus 1 minus ty is less than or equal to e of x plus 1 minus t f of y. And you have to show this, that each of these guys are greater than or equal to any fi and since f is convex, you know that this is actually greater or equal, or less. This is greater or equal to
I think you shouldn't bother proving it, Marcus.
But
I think you shouldn't bother proving it now.
yeah, this is easy, but I'm just being stupid. But yeah, if you use that f is greater than fi and use the complexity of fi, you will reach that this should hold. So then I set the math. Anyway, so this function is complex. You can ternary search on it. And that's pretty much this from ternary search this function to find the minimum value.
Should ternary search, right?
Yeah, it's not a ternary search. Not gonna write search, but for some Lx and y and Rx, you find two middle points, you define the maximum value of I for these two middle points, and then you do the ternary search for x. Any questions? You know? From K, what do you feel yours? So you basically had a trio of words. So you had some words organized in some hierarchy like this, and some of these words are dead. This guy said, and we're doing a real call of this word. So we're going to take some permutation of these words, and we're going to call them one by one. And if when I'm calling one word, I have already called an ancestor of this word that is already dead, then this guy will not be able to respond to the roll call. And the question is basically how many roll calls I save by doing this, compared to actually having this guy responding to every roll call. So this is a big counting problem. Because one way to find the answer would be to just go through every permutation and count for each permutation how many times this happens. Like you call a word, but you already call a word, and assess this word that is already dead. But the problem is that the number of permutations is too high, minus 10 to the power. So another approach would be to calculate the answer for each word. So for each word, let's count for how many permutations this guy does not need to respond. Okay. So fixing an word I need to count how many permutations a dead ancestor of this guy appears first. So suppose the I word has two I dead ancestors. Well, counting the number of permutations where at least one dead ancestor shows up first is hard. It's easier to count the complement. So let's count the number of permutations where the I guy shows up first before every other dead ancestor. Okay. Well, the number of permutations is basically you fix the I guy in the first position, and then you can permutate these QI guys in any way. So first have QI, factorial, and then you have to insert the rest of the words in some order, anywhere in this permutation. So you can choose where this QI guys goes in the permutation. Actually, QI goes one because I'm also calling the I word. And one. And we still need to permutate the other n minus QI plus 1 guys. And we visit n minus QI minus 1 factorial. Okay. So this QI factorial times n factorial over QI plus 1 factorial. Okay. You can reach this result shown in some other with some other combinatorial algorithms. I guess this is clear to understand. Okay, so for each arc, you know that the number of permutations that the ith port is called before any of these data centers is this. So the number of permutations that we actually want is the complement, which is n factorial minus this thing. So now the problem is pretty much over. I just have to sum this over all I and divide by the number of permutations, which is n factorial. So the answer to this problem is actually the sum for all I of 1 minus 1 over qi plus 1, where qi is the number of data centers the ith port has.
Marcos,
Yes.
for calculation that complement of the permutation, I can imagine we have ancestors for ki. Then I can put ki at most at that position and minus n minus m minus and I can't go any further because I must position all ancestors after ki. Then I must make some modifications to the formula accordingly. Okay.
And so you're saying that in the permutation where this guy appears, where the ith guy appears first, the ith guy cannot be on the last qi position, right? That's what you're saying. So the ith guy can either be here or before this. We just have to make sure that the other qi guys have to appear after I. Yeah, I believe there are many different ways to reach the same exact result. This is one of them. Yeah, just for good finding you just have to break this down. Okay. It's hard to not breathe.
Don't worry.
E.
Just don't breathe.
So in this problem, you have to count the number of binary strings of length. And I know. Such that it does not contain any palindromic substring of length k or more. And this looks at first like a difficult problem, but if you look at this at the constraints for k, you see that k is equals 10. Okay. One observation you have to make in order to solve this problem is that if there is a substring of this larger string that is palindrome and has length greater than k, then there must be also some substring of length either k or k plus 1 that is also palindrome. Right? Because larger palindromes can be broken down to smaller palindromes by removing the first and last characters. Right? So if there is a substring of length k or more that is palindromic, then I only have to look for palindromes of length k or k plus 1. Alright? Cool. So do a dynamic programming approach to solve this problem and make use of the fact that the key is really small. In fact, I can use as the state of my UP what were the last 10 characters that I used in my sequence. So let's call f of and some bit math here. What is the number of sequences of length n such that the first digit of characters that this sequence has to correspond to this bit math? Okay. And since we have at most, since we were looking for points of length at most k equals 1, this bit math only needs to store the last k characters. Right? So we have at most n times 2k different states. Right? And for each state, you can just check whether you can add at the end digit 0 to 1. And you can check if this new digit forms a palindrome like this brute forcing with the previous k columns. Not brute force, but just a linear search. There's a new linear check to see whether the digit just the sequence forms a palindrome or not. Okay. So each state can be calculated constant times with the overall complexity, not constant, but of k time. So the overall complexity would be n to k times k. Second,
How do you deal with the even and odd polynomials? Is keeping k enough for dealing with even and odd cases?
yeah, as long as you know what were the last k characters of your string, if you want to check whether the next character can be either 0 or 1, for a palindrome of length k, you just have to check whether this guy is a palindrome, and for a palindrome of length k plus 1, you check if this guy's here is a palindrome. In which case it is, but this is okay.
And did you check if the last k or k plus 1 were palindromes inside the function, or did you pre-process it? Because we got time limit.
I checked for every state.
Okay.
And I did it recursively. I didn't do any of the optimization.
Okay.
Any other questions? Okay, problem J. K combines. In this problem, you have a bunch of rectangles. All rectangles are aligned to the x and y axis. And for each rectangle, you have to find what is the smallest rectangle that contains it. And if there are no rectangles, you can find it. So just for simplicity, let's assume that there is a very large rectangle that contains every single rectangle on the plane. And let's say that the idea of this rectangle is minus 1. Just so we don't have to deal with the case that the rectangle has no parent. Okay. Well, how do we solve this problem? imagine there is an infinite vertical line that sweeps the plane from left to right. We're going this direction. And whenever this vertical line touches some rectangle, we call it an event. And we always process stuff at events. Okay. So the first event that I have to process is this large rectangle. Right. So what I need to do is basically keep a data structure that supports some operation that I'll want to explain later. But what this data structure has to do is basically insert some rectangle with some interval from y1 to y2. And then once my data structure has some rectangles and I need a new rectangle, I have to check which larger rectangle contains this one. Okay. So initially my data structure contains only the minus infinity and rectangle, which has a minus 1. Once I reach this guy, I need to somehow be able to detect which of the rectangles in my data structure contains this guy, and this is the smallest one. And once we reach the end of one rectangle, like here, we just remove this rectangle from our data structure. Okay, there are many different data structures we can use here. So, for instance, we can use a segment tree that allows the following operations. Given an interval, you set all the elements of this interval to the same value. In our case, we need the index of the rectangle. And then another operation we need this to do is when we insert a rectangle, I want to know what rectangle are we in, right? And we can check this by basically seeing what is the value of this element in our segment tree. Right? So this y coordinate corresponds to some position by the segment tree, and I can just check which rectangle this position corresponds to. Okay. So this is one way to do it. You could also use a family tree, binary dimension tree, or binary tree to solve this. But a more simpler way would be to just store the y values in a set. So you just keep an order set of all y's, of the y values of all rectangles that are currently active. So initially we have minus infinity, and eventually we find one rectangle. So once I reach this part of a rectangle, what I'm going to do is look into my data structure, in this case the set, and see what is the first y in the set that comes right after y2. Okay. What is next y3? And I have two cases here. Either this y3 belongs to the lower part of the rectangle, so something like this, or this y3 corresponds to the upper part of the rectangle, in which case you have something like this. Okay. So in the first case, what we get from this is that this rectangle has to share the same parent as this one, right? Because we know that there's some rectangle here that covers them both. And well, this external area is shared by both rectangles, right? So then this area has to belong to the rectangle that contains these two guys. And since this guy is already present in my data structure, this means that I have already calculated the parent of this guy. So if I want to know what is the parent of this rectangle, I just have to check who is the parent of this rectangle. It has to be the same. Another case, we have that this y value is the topmost y of some rectangle. And this can only mean that this rectangle must cover this rectangle. And it must be the smallest one, right? There cannot be an intermediate rectangle here curving this guy. Otherwise, this will be the smallest y that you would have found. Okay. So this is one simple way of implementing this. And didn't need any fancy data structure to solve the problem. All right.
The observation is that wherever we have an event where it opens a rectangle, the next event where it opens another rectangle, that is another rectangle, will be contained inside the rectangle where the previous opening event happened.
Mm-hmm.
That's just it.
No? Because you can have rectangle on top of the other. So when you are sweeping line, you meet the top one and then you meet the bottom one, but they're not inside.
Okay.
Yeah.
But if the vertical coordinates, we have to make comparison between vertical coordinates, wherever we have a new event.
So not necessarily two consecutive events would correspond to parent and child, because as he said, we could have one rectangle starting here. But as long as you keep track of the y coordinates of all rectangles that are present that are currently active, you can easily check once a new rectangle comes in who is the parent by just looking at this y value. Is it actually? Okay. Yeah, you didn't need to have these IDs. You could use any other data structure. It would make implementation harder, but the idea would be similar. So, because it's a question of trade-off. Okay. Problem A, black bears. And this problem we have like puppets. And holes. And you knew for each hobbit, how long does it take to reach each hole? For given a matrix of times. And we want to know what is the least amount of time that is needed such that at least k hobbits get into some holes. Right? And each hole can have at most one hobbit. And we have this weird possibility that if a hobbit arrives in a hole early enough, you could dig a cave for a hole in it, so that this hole would now support 2 hobbits. But this can only be done once. So if one hobbit arrives at a hole, then he can spend seconds of time to dig this hole bigger, and then one other hobbit could jump in. Okay. So given this situation, what is the least amount of time we need to fit 8 hobbits into some set of holes? Okay. What complicates the problem is this possibility of digging a hole. So first, implicitly, let's suppose that hobbits could not dig holes. Well, once again, if we know that k hobbits can fit into some holes in a time t, then we know that this is also achievable for every time greater than t. So we can finally search on the optimal value of time. So now the question is, fixing the time limit we have, we need to check whether we can get k hobbits into some holes. Right. Well, since now we know the time we have to get into holes, we can just check for each hobbit which holes he can get into within this amount of time. You can just see, you can just look up the matrix that's given to you and check if the time that this guy takes to get to this hole is less than or equal to t. If it is, then this is one viable solution. If it is not, then this guy cannot go into this hole. So we just calculate this for every hobbit. Stuff like this. Guess what? We end up with a bipartite graph. And you want to know whether you can pair at least k pair of those hobbits with holes. So this is a standard matching problem. And we solve with our favorite matching algorithm. But this doesn't take into account the fact that hobbits can dig holes. Right? So this is a complication of the problem. And how do we get around that? Well, if a hobbit can dig a hole and it takes C amount of times to do that, then if I have only t units of time to get hobbits into holes, this means that the hobbit that dug a hole needed to have arrived at a hole in time at most t minus c. Right? If hobbit arrives at a hole later than t minus c, he could start digging a hole, but he would not end up on time. So that would be for nothing. So if a hobbit digs a hole, he needs to arrive at this hole at time t minus 0 less. So what we could do here is duplicate this set of holes. And now we add an edge from a hobbit to this special hole, not if the arrival time is less than or equal to t, but if this time is less than or equal to t. This would mean that this hobbit can arrive at this hole and dig a cave. Right? Dig a hole, not a cave. A cave would take 200. And this basically works, right? Because if a hobbit can get to this hole, this means that he can dig a hole and basically free this spot to some other hobbit. Right? So it's easy to see that by doing this, a solution exists if and only if a match outside of this cave exists this modified graph. So the key idea to the solution was to realize that we could adapt our matching solution by duplicating each hole, like creating a special hole for each hole that corresponds to a hobbit arriving here earlier and digging the hole, digging a corner. Okay. Yeah, that's great. It's a cool problem. I like it. Any questions so far? Okay, so I guess we have 2 more problems to go. Let's start with problem H. 4 problems. You needed to know a bit of statistics in order to solve this problem. So basically you have basically a tree. And a tree where each leaf node corresponds to a random variable, a uniform random variable in interval 0 to 1. This is x, y, z. All these variables are independent of each other, and all intermediate nodes will be either a minimum operation or a max operation, which means that given 2 random variables, this corresponds to the random variable that is the max, that is the minimum among these 2 random variables. And you have to calculate the expected value of this random variable. Okay. So this one in this problem was finding distribution functions for each of these intermediate functions, for each of these random variables. So the distribution function for the uniform distribution is rather easy. F of x is 1, and the cumulative distribution function of x of this random variable is x in the interval from 0 to 1. Okay. And we know from statistics that this is the integral of f of x. X is also equal to the probability of some of these variables be less than this is often statistics. If you take a statistics course, you should know this. Should. Okay, so how do we find the distribution of the minimum of 2 other distributions? So suppose we have a minimum operation of random variables C and D. Suppose that we know what is the CDF of these both functions, of these both distributions. X, B, and I want to know what is the CDF of the minimum of these 2 distributions, these 2 random variables. Okay, this is just, I'm going to do some math here. But it's not complicated, it's really easy actually. Let's call this M, I don't know. We want to find the CDF of this random variable. So what we're looking for is Fm x equal to probability m be less than x. But f is the minimum of 2 random variables. So this is actually the probability that minimum of A and B is less than x. I chose it first. I'll read it first. Okay, so I'm going to calculate the complement of this probability, right? If this value is not less than or equal to add, then it must be greater. Right. Okay, but this only happens if both A and B are greater than X. Right. And since all variables in the problem are dependent, in particular A and B are also dependent, so we can separate this into product of probabilities. But this is basically the complement of this probability. Right? Same goes for this one. And these two guys are the CDFs of their corresponding functions. So this is actually equal to 1 minus okay. And we know that the CDFs of the uniform distribution is a polynomial on X. So by an inductive hypothesis, by an inductive argument, the CDF of every single distribution in this tree will also be a polynomial on X because the product of these two children. This is a polynomial, this is a polynomial, so this is a polynomial. So the CDF of every distribution in this tree will be a polynomial on X. Okay. So finding these guys is easy. You could do the similar math to find the distribution of the maximum. And you find that is the product of both CDFs. This is for X. So by doing this, you could find the CDF of the distribution here at the root of the tree. And once you have the CDF, finding the expected value is pretty straightforward. You can use the definition of expectation. You could do this. So you would have to first find the derivative of the CDF, multiply by that, so that integrate. Or you could be a bit smarter and integrate this by parts. This is X of X, so this is 1 minus.
You should know it because you went to calculate.
This is X, okay, the solution is here. And this is 1 because f of 1 is 1, and x is 1, so this is 1 minus the integral f of x dx. So you didn't have to find a derivative, multiply by x, and then integrate it, and do this. You can just integrate f to find the answer. Yeah, that's pretty much the solution. It's just pure math.
Do you know if a numerical integration would work in this problem? Or
I'm not sure. Probably not, because I think the statement warns you to use long double and long long. So this probably means that you would probably have some precision problems along the way. But by doing this, you wouldn't have to worry about that because this is a polynomial, and integrating finding the primitive of a polynomial is easy, especially when you find the definite integral of 0 and 1. You just have to substitute. So x is 1, so you just have to substitute x by 1. This is pretty easy to do. An easy way to implement it is to define a strict polynomial, define difference product and sum of polynomials, and then just do this stuff that we did. Okay? I guess we can have a break, and then I'll play problem F and data structure just use.
Happy Valentine.
Okay, let's move on. Final cross problem F. Deck permutations. So yeah, this problem is pretty cool. You have a deck that initially contains every number from 1 to n.
Então, aquele que eu dava, que eu sabia. Então, acho que
And at each step, you could either pop one element from the front of the deck or from the back of the deck. And this will generate a permutation of these n numbers. So let's pose at 6. One possible permutation would be 1, 6, 5, 2, 4, 3, for instance. So for this step, you could either take the first element or the last element remaining in the deck. And well, the problem is more complicated than this. So first, the first thing that statement defined is that it attributes to every permutation number, which is the index of this permutation if you take all permutations and order them lexicographically. To make the problem even harder, you will not be given some full permutation at first. You will be giving the first n over 2 elements in some random order, and you would have to determine what is the minimum and maximum value for this guy at each step. Okay? So there's a lot of things going on, so you have to approach this problem step by step. So the first thing you have to think about is how many different permutations can you have at the end of your at the end of this process. Well, at each moment you have two choices. You either pop the element from the front or the back of the deck. Right? And as long as the number of elements remaining in your deck is greater than 1, both these options will produce different permutations. Right? So if my deck has n elements, this will mean that the total number of permutations is 2 to the n plus 1. Right? Each possible choice of front or back that you take leads to a different permutation. Okay? Cool. So this is the total number of permutations. Now, the next thing you have to think about is what happens if you choose to take the element of the front of the deck rather than the element of the back of the deck. So those are our current permutations 1, 6, 5. And I want to choose my next element. So this guy could be either 2 or 4, right? If I pick 2, I will get some permutation depending on what choices I make. And if I choose 4, I will get a different permutation. But the important thing here is that every permutation generated by this choice will be greater than any permutation by this choice. Right? Because the element we chose is greater. Right? So let's assign for each permutation a string of zeros and ones that basically represent what choices I made at each step. So so for this substrate, this would be 0, 1, 1, 0. So whenever I pop an from the front of the key, I add a 0 to the sequence. And whenever I pop an element from the back, I add 1. Okay. So each permutation will be assigned to a different string of n minus 1 bits. And the cool thing about this is, due to this property, if you take a string If you take a permutation, look at the string that assigned to it, and interpret this number as a binary number, it will actually coincide with the index of the permutation in lexicographical order. Right? This is 0, 1, 1. If you pick 2, you're adding 0 here. If you pick 4, you're adding 1. And this guy has to be greater than every one of this guy. This permutation must all be greater than these permutations. And here you have and 2 to n minus 3, 4 choices. So if you do, it's not easy, it's not hard to see that this is true. Right, just do some math and it works. Okay. We're not even half done yet. But this observation is important. So now what we need to think about is what information you get by knowing that at a certain position of your permutation there is number 5. Well, if you know that the number 5 is here, we have 2 options. Either this 5 came from either you pop this 5 from the front of the queue or the back, or the back of the deck. Right? But since we are only looking at positions that come before the first and over 2 elements, actually only one of these possibilities can be true, can happen. For instance, for 5, it is not possible to reach 5 from the front of the queue using only n over 2 operations. Right? You need at least 1, 2, 3, 4, 5. So if you know that number 5 comes in this position, you know that it came from the back of the deck. It goes for any number. If there is 1, 3, number 3 could not have come from the back of the deck because you need at least 4 operations. And my sequence has 96. So the fact that the problem only gives you the elements in the first and number 2 position is important because this means that there's always one possibility from which direction each number came from. Alright? So this is really important. So by knowing from which direction each number came from, I know exactly how many pop front and pop back operations I need up to this point. Right? If this is a number 5, I know that in order to reach 5, I need 2 pop back operations. So I know that in this prefix, there are exactly 2 pop back operations, and the rest of the operations must be pop front operations. So we have 1 pop front and 2 pop back operations. So, or in our code, this would be 1, 0, and 2 1s. Okay. So each element that the input gives you tells you for the prefix of your binary string how many 1s and 0s are there. Is that clear? This is basically the key observation of this problem. So now let's process each element at a time. So at first, you have no information whatsoever of your permutation. So the minimum possible value is all 0s, which is 0, and the maximum value is all 1s, which is 2 to the power minus 1. Okay. Now, as I just mentioned, when the input gives you a number and a position, you get information for this prefix about the number of 1s and 0s in this prefix. So in that case, I know that here we have two ones and 1 0. So if I know the first 3 digits of my string, among these 3, 2 are 1s and 1 is 0, what is the minimum number I can achieve? I have to put 2 1s here somewhere, right? And the minimum number I can generate is like by putting 1s to the right. That 1 0 here. And I don't know anything about this guy. This guy can be anything, so I can just fill out without also generating both 0 zeros. So this is the minimum permutation that satisfies the given input up until now. Okay. Same goes for the maximum. Maximum value is 110, 111. Okay. Cool. So you will be given more and more information about the first half of your permutation. And each time the input gives you a new pair value position, you get new information about the process of your binary string. So you can keep track for every prefix how many ones are there in this prefix. So in our example, we know that here we have two digits ones. And I suppose that this position is 1. So we know that here we had exactly one pop operation, one pop operation. So here that could be only one digit 1. So at any point of your algorithm, you will have this information. For every prefix, this continues. For every prefix, you know how many digits ones there are there. Right? So, and for a consecutive prefix, you can calculate the exact number of ones that has to be in this interval. Right? And for each such interval, since you know the number of ones, you can find what is the minimal value and the maximum value for each interval. Right? So you can just keep track of the minimum value so far and the highest value so far for each interval. And whenever a new pair value position comes, you need to update this structure. Right? So you have 2 cases. Either the longest prefix you have information about is here, and you gain information about the prefix that comes after. In this case, you know information about this segment and just compute the new minimum and maximum value. Or the information you gain is about some prefix that comes before the largest prefix used so far. So this means that this guy will fall in between 2 prefixes that you have some information about. So if you have the answer for this interval calculated, you can just subtract from your current and lowest index and highest index the answer for this interval. You can split this interval into 2 parts and then recalculate for each interval. So each information, each line of input, for each of those lines, you only have to change the constant number of intervals. So each update can be then come time. Yeah, that basically solves the problem. The only thing that's left to do is given an interval of positions from L to R and have k digits 1. How do you calculate like this value? It has k digits to the left or k digits to the right. But this number can be easily found. This is like 2 to k minus 1. this maximum value, you can just calculate this value, multiply, you can shift this by the number of conditions you needed to shift, and you can easily find this value. And the same for this value. So with all this, you should be able to solve the problem. Any other questions? Cool. So let me explain the final thing about denominator tree, which is the data structure we need to compute some denominators and stuff. Can I read my notes? So recall from last class that we need a data structure that supports two different operators.
Você tirou o carregador? Que cara trouxa. Aí, tá tudo ótimo. Não, pode.
Eu usei posições de comparação. Tem que fazer
Não é não. Olha que porra.
Okay, so we need a data structure that supports these two operations. It might look magic, but actually, the data structure that solves this is really, really similar to the unified data structure. So what you have initially is a forest of trees containing single elements. What will happen is that I'll start linking two different trees, and I want to calculate something about this tree. Okay, so link VW is super easy. So let's store in some array who is the immediate parent for each vertex. Okay. In our algorithm, we will always link a vertex that has not been processed to the vertex we just processed. This means that V is always the root of some tree, because it has not been processed. So link VW is fairly straightforward. Just set the parent, ancestor. I'm gonna call ancestor, because otherwise the parent would be confusing with parent ECFS tree, and so on. So let's call ancestor the parent of a node in our data structure. So for me to link the you just set ancestor W. This is link. Super hard. Really, it's just this one line here. And this is like really similar to the union operation of schema. So just like the eval operation, we really similar to the find operation. So what does eval have to do? Given a forest, this is root tree, and this is B. We have to return what it's asking us to return. Well, if V is the root of some tree, let's define that the ancestor of a root is -1 by default. Okay. So for this first condition, we can just check whether the ancestor of V is -1. If that's the case, we just return V. Okay. So for the second case, what we need to do, one naive way to implement that is basically going up in the tree one by one, keeping track of what is the vertex whose semi-diameter has the lowest pre-ordered index, and return that. Okay. But that's pretty stupid, and that's quadratic, like linear time, worst case. But you could do better. Instead of doing that and just returning the value, what we can do is the same idea, we can apply the same idea of path comparison in G5. Once we find the answer for this vertex, we can store this answer, the optimal view, in some array, let's call it label. So just go up in the tree, keep track of what is the optimal view you've seen so far, and store this in the position V of this array label. Okay. Now, the next time you call eval V, you don't have to look at these guys again. You already pass through them. You know who is the lowest, who has the lowest, who has the semi-diameter with lowest reorder. So you just need to return label U. And since we have already passed through these guys, there is no need for the ancestor of V to be this guy. You can just set the ancestor of V directly to this guy. And now, if I call eval this guy, for instance, what we're going to do is not look at the semi-diameter of this guy, but we will look at the label of this guy. So the label already stores what would be the optimal view in this path that this guy would follow. But since we already done this job by calling eval this vertex, we don't have to do that again. Okay. So that's the main idea of the data structure. And implementation is really easy, it's like 5 lines. If ancestor -1, this means that V is the root of some forest, and we want to return V in this case.
Sim. Acredito que sim, porque agora vai começar teu curso. Assim. Tá dando curso, agora vamos ver aqui.
If the ancestor of V is -1, this means that V is pointing, the parent of V is a root of some tree. Right? And we don't want to consider roots when we're finding the optimal U. So this will be the base case for the eval function. Just return label of v, and before processing this, we set label of every vertex to itself. Okay, that will be the initial value of the label. Okay, otherwise we will just implement path compression. So the first thing we want to do is call eval on the parent. So let u be zone of the cluster v. Now this guy is holding the optimal u, the path from the parent to the root. So the only thing we have to do is check whether v is actually better than u or not. If preorder and label of v. Preorder as u. In this case, v is actually a better u than the u for the parent. So just set label. Actually, you don't need to set anything. Label of v will be whatever case. So let's make this. So if this happens, then I can improve label of v. Just set label v u. And now we don't want to do this whole thing the next time we call eval v again. So we just set ancestor of v to be equal to the ancestor That's because if we call eval on the ancestor of v, by the invariant argument, we know that the ancestor of v will be pointing straight to the root of the tree. So ancestor of v will be the root of the tree. So just set ancestor of v to that. Is that clear? That's pretty much it. Return label v. And since I said that this structure is really similar to Unify, you might be wondering whether we can also implement union by rank optimization here. The answer is yes. You can. The paper that I was reading explains how to do that. The thing is that the link function gets more complicated. It would like to be the same length as eval or even longer. And the author of the paper did some experiments with running times, and apparently the optimization doesn't make it much better. The improvement is less than 2 times. So in practice, it's not really worth to implement even by rank. And this is actually enough. And since it is really similar to Unify, their complexities are actually the same. And it's possible to prove that after n-1, or after n calls of the eval function and the link function, the overall complexity doesn't exceed n plus e times log v, which is basically the same complexity for the Unify. So the overall complexity for the semi-dominator tree is actually this, because the bottleneck for the dominator tree algorithm is these eval functions and link functions. All the other operations are constant. Back here. Any questions about anything? Alright. We can just go to lunch.
Passou?